by the speaker, one friend Ziquan Zhuang from MIT. Ziquan will speak about boundedness of singularities and technology of Kollár.
So first of all, thanks very much for the introduction and the invitation, and happy birthday to Professor Schaffer. Right, so let me just read the title already. I'm going to talk about boundedness of singularities and the minimal log discrepancy of Kollár. So everything is all going to be over the view of this. So let me start by motivating somewhat question. So in directional geometry, there's a well-known local and global analogy, where on the local side we put this object called KRT singularities. While on the global side, we have the Fano. The Fano is the map condition, so we only have KRT singularities. I'll just write Fano. Okay, so if you want to go from one direction to the other, for instance, starting from a global Fano object to the KRT singularities, it's just a usual Fano construction. Starting with the Fano variety, I can convolve it and it can also polarize and end up with a KRT. You can also go backwards, and starting from the Fano KRT singularity, there's a construction called the Kollár extraction of a Kollár component, which I'll explain later in my talk. Roughly speaking, over every KRT singularity, you can extract a Kollár component, and using this component, you can actually degenerate it towards like a cone singularity, orbifold cone over this. Right. So, but then because of this analogy, it would be an interesting question to say if you have something on the global side, we may want to ask, so what would be the analog on the local side? So, for instance, one question on the global side that's for typical international geometry would be boundedness questions. Suppose we have a class of objects like Fano varieties that we are interested in, whether they are parameterized by finite parameters and also finite varieties. So, and even more, you can ask about moduli space. So we do have a moduli space of Fano varieties called the three moduli. And of course, boundedness is the first step in constructing a moduli space. So then we can ask, right, so what would be their energy in the local case? Right, so in this talk, I'm just going to focus on boundedness. We can contemplate about what would be the analog of three moduli. I don't think I'll focus on this. Okay, so now what would be the kind of bounded result we'll be interested in find analog in the global case? So there are two boundedness results that I want to focus on. So the first one is the theorem of Kollár. It says that so let's fix a dimension. Some integer. And normally when you fix some numerical invariant, so in this case, let's just fix some positive number. Then, if I look at a set of Fano varieties of this dimension, and the condition is that this Fano variety has a so-called epsilon KRT. Let me write down the statement first. So, then this set is so they belong to finitely many families. So we're so I guess a lot of you knows what this condition is already, but this simply means that the minimal log discrepancy is at least this number. I guess this term has been defined a lot of times in this conference, but I'll give a more precise statement. Dimension, yes, and dimension. Next. Okay, so that's the first statement. The other statement comes from case stability, and that's what really goes into the K-model construction. Although the original proof also relies on this. Okay, so the original statement was due to Chen Jiang. There's a different proof given by Jiang and myself, which doesn't rely on the statement. So the result is that, again, if I fix a given dimension, then when I look at the set of so-called semi-stable Fano varieties, I don't forget the dimension this time. Semi-stable n-dimensional Fano varieties. So this set is also found. So for this talk, the precise meaning of semi-stable is not that important. So you can just think of it as roughly saying that it has k-lines dimension. Also, this term has been defined in further couple of talks in this conference. So we have these two precise statements. Now the question is, what would be a local element? Bounded volume. Yes. Sorry. Yeah. I was forgot. With volume at least A and least B. So this is just the top self-intersection number of the n-economical distribution. Yep. Thanks. All right. So there are several issues if we want to consider the local analog. So the first issue is what's the meaning of being bounded? And if you want to look at the second statement, for instance, there is also a question of what do we mean by a semi-stable or KLT singularities, and what do we mean by the volume of the singularity? Okay, so let me try to answer these questions one by one. So first of all, what should boundedness be? So there is a slight issue here because if we consider global varieties, and especially when we're thinking about moduli questions, the deformation space has finite dimension, but that's no longer true for singularities. So the first issue here is that the deformation space of even a KLT singularity can be unbounded. So we can have infinite dimensional deformation. So for instance, the easiest example is if you take this horn over a singular project. Okay, so this lives in C4, but when you deform it, you can add the emission variable. So any power, everything stays KLT, but then because this power can be arbitrarily large, the deformation space is no longer finite dimension. So then if you want to find a finite dimensional family to parameterize this singularities, you would fit. But there's a way to fix this. So the trade-off is to consider notion of special boundaries. So instead of saying that all the singularities are parameterized by a finite dimensional family, because it seems that the problem here comes from this deformation step, I'm just going to say that a class of singularities is specially bounded if they all isotrivially degenerate to a really bounded family of singularities. So if they isotrivially degenerate to a bounded family of singularities. a bounded family really means I have a family over a finite type base where the fibers are KLT singularities. Okay, so maybe I should say, if I ever forget, every singularities in this talk will be KLT. KLT. This can be made more precise, but I think I'll just use this definition for this stuff. Sorry? That's right. Yeah. So once you have a specially bounded family, actually a lot of invariants will be bounded. All right. But as you see, it doesn't mean that the family itself is. Okay. So for instance, here you can just add the extra parameter t, and when t is not 0, you get the same singularity. But when t is 0, you get this one. So this will be the bounded one. This is the specially bounded. Okay. So that's the boundedness part. So now if you want to make this more precise, so one way to make this even more precise is to go back to the original direction, how do we go from local to global, right? So for every KLT singularity, one can extract this Kollár component. So maybe another way to say this is that I want to have a procedure to extract Kollár component, but those Kollár components only live in the bounded family. So that's another way to say it. But let me first define what's Kollár component. So let's say I have a KLT singularity. So X is my variety, this is my singular point. Then a Kollár component over the singularity. So consists of the following diagram. So first of all, I have a birational morphism, a proper birational morphism. That is an isomorphism away from this singular point. And then there will be an exceptional divisor. Exceptional divisor. And the assumption that has to be satisfied. So first of all, this is the unique exceptional divisor. And this diagram, so that is it's relatively anti-ample. It actually implies that it's exceptional, unique exceptional. And I also want the singularities to be mild. So this pair y comma e is KLT. So what this implies, for instance, is that, right, so I can do a junction on this component. So if everything's smooth, I just get a canonical bundle of E. But in case it's singular, I get a direction term of the different. And these assumptions together would imply that this pair, E comma delta, together with a different divisor, this is a KLT Fano word. So this is the kind of Fano global object that associates to my KLT singularity. And this thing always exists. So this thing, the distance is due to JAMI for any KLT singularity. But it's not unique. Sorry? Yeah, actually it's the close point. So in that case, we might want to localize, but let's say for this talk, X is the close point. No. Yeah, but even if it's not isolated, one can still extract such kind of Kollár component. Yes, you can take con over a singular Fano, but it's still KLT. But it's not an isolated singularity. But then the vertex plot will give you the Kollár. That's are there more questions? Right. So that's basically how we associate the Fano KLT singularity. But because it's purely loggically, it comes with a choice. So if you want to make the definition more precise, we can just impose the condition that I want to get bounded band equality. So actually, a more precise definition that somehow gives the analog of Berka's statement was given in a paper by So let me just use that definition. So hopefully work. They make the following definition. So let's say a singularity is so-called epsilon delta log if I can find a component, precisely the exception of a Kollár component. Here it comes to this diagram. And my requirement is that first of all, the epsilon R refers to the minimal of discrepancy, which abbreviate as analogy from now on. This is epsilon. And also, when you look at this KLT, in the definition, we just require this to KLT. But at this moment, you want this pair to be also so-called delta KLT. Which means that once you look at the log discrepancies of exceptional different letters this time. So if I look at the log discrepancies of the dividers over my y, this has to be at least that's the definition. But again, using a junction. The second condition simply implies that, so if I look at a Fano pair, the global objects that I get from this construction, then this will be delta KLT log Fano. So it's exactly the condition that shows up in Berka's theorem. So whatever that is. So, so using this definition, one can at least give an analog of Berka's result. It's because it's just defined in this way. Right, so basically, I can show, and this was done by Raga. So just to distinguish two different views in this talk, I'm going to say this view. Okay, so for instance, they can show that if you fix your favorite number, so n is your delta, I mentioned, and then you guess what this corresponds to. Then the set of epsilon delta log canonical. Okay, so maybe it's the last side we get very close. But that's just a time. So, what? Anyway, there are some inequalities, but the name doesn't matter that much. Yeah. Yeah. It's your choice. So. Mm-hmm. Sure. Yeah. Okay. Yeah. Anyway, so let me just say, so this set of KLT singularities. Especially bounded in the sense that defined on the right. Just on the right, maybe top right. So basically, because we are able to extend a Kollár component, which satisfy the conditions in Merca's theorem. So it forms a bounded family to degenerate the point over that bounded family. That's the special degeneration, or the isotrivial degeneration. Okay, so that's. Now the question is, can we find an analog of that statement for a semi-stable Fanos, which concerns more global conditions? There's this volume condition, and there is also this condition that has connection to Taylor-Einstein matrix. So fortunately, there's an analog for that volume condition, and this invariant is called the local volume of a singularity that you have already heard in Chen's talk, but I guess not every one of you was already there. This invariant was defined by Shuli. Let me quickly sketch the definition. So the basic diagram is very similar. So yes. Yeah, I think this is basically based on.
This special boundedness space, boundedness of the K.
Yes. That's right. So I guess I didn't put it in a more precise way, but so in the precise definition, you require this family to just be Q constant, actually. So. Okay, so I guess I need to define the local volume of the singularity. So the basic diagram is the same. So we have to consider isomorphisms that resolve the singularity. This time, I don't require this to be a Kollár component. You can take any lockless solution, for instance, and any divisors that appear above that maps to your singular point x. So this can be any lockless solution. So with this diagram, there's already one basic invariant that we can associate in directional geometry, and this is exactly the log discrepancy. So this is 1 plus the order of vanishing along this divisor E of the relative canonical divisor. So I take ky minus the pullback of kx. I want to look at what's the vanishing order along my exceptional divisor. Another classical invariant is the volume of this divisor. So this can be defined as follows. So it's going to be the growth rate of a number of sections. Okay, so let's say I look at OX, but I model so this like the local functions, but I want to model by the ones that vanish of order at least n along my exceptional divisor E. Okay. So the co-length of this will grow like m to the dimension. So I take the leading coefficient of the asymptotic. Okay, so that's the dimension of the system. Avoid writing too many numbers. Right. So this first row is really just the functions that have vanishing order at least. Right. So this is the asymptotic growth rate, growth speed, I guess. Right. So then this gives me the volume of this divisor. It's like a multiplicity. Right. So if your E just comes from the ordinary block of that singular point, then this is really computing the multiplicity of the singular. Now, so these two are more or less classical. But Shirley came up with this idea from his work on K-stability that a better invariant is to look at, which is called the normalized volume.
And this should be defined, right, by multiplying these two numbers in a specified way. So I take the volume, but I want to normalize it using the nth power of the log discrepancy. I mean, you can somewhat explain why you have to put this power here. So the reason is that I want to make this, in some sense, homogeneous of degree 0. Because later I want to take the infimum of this. So I'm not going to say precisely what this means. You have to extend this to the evaluation space, but just to give you some idea. If my x is just a smooth point, and my E comes from a weighted blow-up. So it's a weighted blow-up with weights equal to, let's say, a bunch of integers. So the dimension is n, so I need n different ones of them. Right, so in this case, the log discrepancy of this weighted blow-up, these are just integers. It's just the sum of all the weights. While the volume turns out to be so 1 over the product of all the weights. So in some sense, this has degree 0, this has degree -n. So when you multiply them this way, you get a rational function of degree 0. Okay, so that's what I mean by homogeneous of degree 0. But you can make this more precise in general by using evaluation space. Okay, so but that's the idea. Right. So the next one. So then, so the definition of this local volume, I can just continue here, of a singularity, of a chaotic singularity, is just by taking the infimum of all these normalized volumes. Any log resolution and any divisors that appear on a resolution that max to the singular. Okay, so at least that's the definition. But if you haven't seen this enough times, maybe it's easier to see some properties and some examples. So some of this will essentially be stop. So for example, so this is really an invariant analysis of similarity. So should we show that for any chaotic similarity, this number, this local volume is always positive. And actually, it's exactly positive when it's there. You can define this one like that because it's not going to be there. So it actually gives you some unshifted. So the infimum does not go to the zero when you do it in this way. On the other hand, you cannot grow to other extreme. So we can have shown that so this local volume of chaotic singularities is always at most at the end, where this is the local volume of the smooth point. So actually, for smooth point, you can just take the ordinary block, which corresponds to the weights all being 1. So log discrepancies and volume is 1. So you get n to the end. And that's the local volume of the smooth point, and that's the biggest local volume. Yeah. Actually, exactly what it is. The general expectation is that the more singular point you have, the smaller the local volume. Next thing, and as you know, there are other invariants of chaotic similarities, and you can actually compare them with this local volume. So one invariant that's quite well known is the log discrepancy. So I guess I haven't really defined it officially, but
the minimum of discrepancy of a pair of similarity is defined as the smallest of discrepancy from that among multipliers. So it turns out that this is always at least bounded from below by the local volume up to a dimensional constant, which is and this was proven by vigilance. Oh, sorry. So in some sense, you can always compare them to the minimum of discrepancy in one way. On the other hand, it also looks finer than the minimum of discrepancy in some situations. So, for example, the reason it's called volume is because when you do a function, this thing will just get multiplied by the degree of the function. So maybe I will just write down one example. So I guess this was proven by if you look at the volume of a quotient singularity, one space multiplied reaction that's fixed on 3 dimension 1. Then the local volume of this is just the local volume of the point space divided by the group volume. So for instance, if you look at 80 singularities on the surface, the minimum of discrepancy is always 1, but this volume you can really go to 0. So this local volume in some sense is a finite. And because of this, it was conjectured that so if you fix a local volume, the number of the family of chaotic singularities that has that local volume as the lower bound will not determine. So they will be specially bounded in the sense that I described. But before I do that, so then there's one last example I was mentioned, which is that so why does this relate to case stability? Because the earlier statement I would define analog actually involves case stability. So actually, if you take a confidence function, so let's say D here we follow the is one over. All of it should be the test. Then the local volume of this whole point will be equal to the volume of this Fano variety of some intersection number. Actually, take the cone with respect to every one. So then this should be equal depending on if the Fano variety is case sensitive. So this provides the and actually this was one of the motivations for I think this was proven by during some special case, the zero one is really. Right. So in some sense, if you take all of the case study scale of varieties, this local invariant exactly recovers the global volume that we have. But in general, if it's not case study scale, this kind of thing. If the same happens. So if you can find a Kollár component that's case study stable, then the volume is computed. Okay, so I guess this somewhat gives the analog of the global volume for the statement that we want to face. Okay, so then there's this last question, which is so what would be a case semi-stable similarity? So the short answer is that it is expected that every pair of similarities is case sensitive. So So the reason is that there is a stable degeneration conjecture. So I'm going to put this conjecture in the abbreviated form. So roughly speaking, the conjecture says that every chaotic similarity has a canonical degeneration, canonical isotrivial degeneration. Test considerations. Who the so-called semi-stable Log singularity. Actually, I'm not going to define precisely what this means. I want to get what semi-stable is. In fact, this degeneration, the fact is canonical, is actually induced by so this increment usually is not a minimum, but it's going to be a minimum on some valuation space. So it's going to be induced by a minimizer of that. But the thing to take from this conjecture is that we do expect every chaotic singularity to be case-sensitive in a pseudo sense. So in some sense, if I want to find an analog of the statement, hopefully it's still there. Not Kollár component, but some Kollár variables. Because this integral becomes an integral. So it only becomes a minimum after extending this normalized volume function to a valuation space. I didn't do that this time. That's most of it. So that means, at least if I want to get a replacement of this statement, all right, so in the definition, somehow this con part involves the choice of like a real vector field. You can think of this as a C star action. So if you choose the correct C star action, every torus singularity will be case-sensitive, up to choosing the correct C star action. Because in some sense, there is no other degeneration. Yes. But I'm sorry, I don't want to be precise. It's like, so if you want a rough idea, is that if you think of this singularity as the corner of a funnel, you want that funnel to be case-sensitive. So by choosing a different C star, actually you get a different base. If you choose the correct one, then. Okay, so how much time did I have already? So when did we start? Okay. Right. So that means if I want to find a replacement of this statement, I'm going to fix these numbers. I don't need a semi-stable. I'm going to replace Fano varieties by chaotic singularities. I need to replace boundedness by special boundedness. And I need to replace the global volume by this local volume we just introduced. So maybe I should just wait it here. discuss it. Okay, so that's the. So unfortunately, it does not follow from the global case, and actually, it's pretty far from the global case. All right, so that's the first version of the statement. But if you still remember the more precise version that I introduced earlier for the Berghoff statement, so actually, so you can put this in the more precise form. So the more precise conjecture is that I can trace this. Again, you hear this in James Parker. Is that so? If I look at the singularities, whose local volume is bounded from below, then this set of singularities is roughly the same. Well, it's equivalent to the set of singularities which are epsilon delta logarithmic KLT. I put it in the vague form, but this statement really means that, right? So if the local volume is bounded from below by some positive constant, then you're going to define this epsilon delta that only depend on V, such that all those singularities satisfy the epsilon delta KLT condition. And conversely, if you have this condition, you can find a V that only depend on this, such that the local volume is not. So okay, so very good question. So this is one way to make that special boundedness precise. But the second way to make this precise is that suppose I have this canonical isomorphic degeneration. Then what I want to say, this is how you make that boundedness special. So a separate conjecture would be to say that so the set semi-stable log Fano on similarity with volume bounded from below. So this isomorphic degeneration it actually preserves the local volume. Preserving this number doesn't change. So if this set is bounded, then of course there are only finite numbers.
This is where.
Yes. Yeah. So for instance, if this is true, this will imply the ACC conjecture for this local volumes that mentioned in the transfer. And actually, this will imply that the only accumulation point is. All right, so hopefully I introduced the question. So now let me state the theorem. So the first main result I can prove is that, right, so I won't be able to get this statement, but at least I can show that the following two sets, they are equivalent. So on the left hand side, I put this local volume lower bound together with another invariant, which I'm going to call the minimal log discrepancy of Kollár component. And you can guess what it is. Okay, so this is, so the MLD is the minimum of log discrepancies among all dividers. For this, I'm going to restrict to only Kollár components. These are the Fano objects that I can associate to the similarity. Okay, so I also need this number to be bounded from the then this is equivalent to the range. So again, I hope this statement is self-evident. So this two should depend on this two. If I go from the right hand side, like this two should depend on this. So yeah, I'll make it depending how much time I have. Right, so so now it would be very tempting to raise the following question. So of course, this conjecture says that we probably don't need this. And actually, this might remind us of one of the conjectures made by Shopra. that, right? So Shortgraph conjecture that for any singularity, the minimal of discrepancy is at most the dimension of X. So it might be tempting to ask, okay, so are these numbers also bounded from above by the dimension? So this can be a question. So minimal of discrepancies found above by some constant that only depend on the dimension. And so the tricky thing here is that so obviously not every minimal Doppler discrepancy is computed by a Kollár component. And here's an easy example. So if I take this canonical threefold singularity, in C4, then so its minimal of discrepancy is actually 1. So it's canonical, you can just plot the vertex. And when you plot the vertex, you don't see this term. The exceptional divisor is the cone over elliptical. So that's not KLT because it has this cone over elliptical singular point. So if you want to get a Kollár component, you have to do a further plot. So actually the minimal of discrepancy of Kollár component is given by blowing up a point on that further exception resolution. So the number you get is 3. Yeah. And actually if you do a different cone over elliptic curve, like this one, you can make the minimal of discrepancy of Kollár component even bigger than the dimension. So that's why it becomes more tricky. So let me just mention that, but nonetheless, in dimension 3, we can say a little bit more. In dimension 3, we don't need that statement, that minimal of discrepancy. So in dimension 3, so first of all, if you fix the lower bound of the local volume, this would imply that the minimum of discrepancy of Kollár component is bounded from above by some number that could depend on the local volume. So in particular, this implies that maybe I should get this the name this conjecture in dimension. So I feel I'm a little bit out of time, so let me just quickly say that. So the proof actually is a bit tricky, so it relies on the notion of so-called special complement that is a refinement of the Euler complement that Shortgraph introduced. Which goes into the proof of, for instance, the construction of K-model, etc. So maybe I'll stop here, but I'm happy to take questions.
So maybe one, but can you make an assumption of limiting K bounded above by having like a bounded weak like canonical?
Okay, so let me see. For this one, I don't know. So I think it's the proof I don't think it extends to that. Okay. Yeah. Yeah, but of course, in general, we don't expect that this condition is unnecessary. So it's just the proof I have to say.
One question. So you mentioned here that the A might depend on the volume, does it? So
well,
is
so
there a bound on the
right. So okay. So like for my proof, it might depend on the volume, but I don't have examples where it really does depend on the volume. That's what I can say. But maybe one thing I can remark that that really makes things a little bit different from structure of the conjecture for NLP is that if you so I talk about everything with zero boundary, but if you do add a boundary, then this is definitely depend on the coefficient. Really depend on the coefficient. So there are actually examples by adding a boundary. So I think if you just take C to 1 over A, X to A plus E, there's only one Kollár component. The MLB of Kollár component is actually A. It can go to infinity and depend on the coefficient. But I don't have examples that depend on the coefficient. Actually, I don't expect it to depend on the coefficient. Yes.
No more questions. This was things you got. Half an hour before.